So I'm very happy to be here on this very special occasion and this very special Lagos edition. And as we heard on Monday, Lagos started essentially in 2001 with the first GRACO meeting and the SIMPA school. And this was the first time. At that point I was a postdoc with Bruce Reed and he invited me to GRACO. And this was really a very important conference for me because it was the first time I come to Brazil. I met my wife, so you see one outcome of GRACO 1 making noise and running around. I met all the Brazilians, in particular Jaime, and then we started to come to Brazil regularly, and we had a very successful project which brought many PhD students also to Germany for sandwich PhDs. And two of the very good ones that came to Ulm are sitting here. It's Weverton and Vinicius, and many more collaborations have been done. I looked it up on DBLP to have the number. So in fact, me and Jaime, we have 36 joint papers. I was actually surprised that this many. No? And Jaime is a wonderful colleague and a very, very good friend by now. And I have very nice memories of doing research with him. The nicest one was probably when he invited me to his sitio, which is a small place in the middle of the woods, no electricity, no running water. And we did a paper on interval graphs there. So we had a broken old blackboard, some small pieces of chalk, and it was like you couldn't Google anything. You had to do it with daylight or candlelight. And if after some research you were a little sweaty, you had to go down to the river to get a shower. It was wonderful and really excellent. So I'm really happy to be here and thankful to speak on this occasion. So I gave a talk with the same title in Haifa, but so Jaime was there and Marty was there. But don't worry, there is overlap, but there's also some new material in it, especially some joint work with Jaime. So here are the co-authors. So it's two co-authors from the LIRM in Montpellier, Julien Baste and Ignacy Sau, which is also here attending the conference. Then there is a PhD student, Maximilian Fürst, a master student, Marilena Leicht. Here is Weverton. Here is another PhD student that visited Ulm, Carlos Vinicius, and of course Jaime. And I will speak about restricted types of matchings. So you all know what a matching is. So it's a set of pairwise disjoint edges. And we say that a matching is perfect if it covers all vertices. And the set of edges covered by a matching M will be denoted by V of M. So this essentially introduces the notation. And then the matching number is the largest number of edges in a matching. And if you look at a picture, then you have the edges, independent edges forming the matching. The set of vertices Vm covered by these edges, and then you have the remaining vertices. You might have some edges additionally within Vm, some edges outside, and some edges between the two sets, the outside world and Vm. And if you look at this picture, of course, since this set is not independent, the matching wouldn't be of largest possible cardinality. You also have, with every notion of a type of matching, you have an edge coloring notion. If you just take the classical matching, the edge coloring is an edge coloring is a partition of the edge set into matchings. And then you want to use as few matchings as possible, and this gives you the chromatic index, which is the minimum number of matchings into which you can partition the edge set. And since in an edge coloring, every color class has at most a matching number many edges in it, and you need this many color classes, you have this inequality because you have to assign a color to every edge. So this tells you in some way that typically lower bounds on the matching number give you upper bounds on the chromatic index or are related to upper bounds on the chromatic index and vice versa. The history of matchings is essentially the history of combinatorial optimization and graph theory, because apart from Euler's contributions, really the first papers on graph theory were like in the late 19th century by Petersen, and were already about matchings. And if you look at this short overview, it's essentially a really historical overview of the evolution of our field. You have the classical contributions of the Hungarian school, Koenig's theorem that the matching number equals the vertex cover number in bipartite graphs, which foreshadows many important developments like LP duality, total unimodular matrices, integrality of polyhedra. This is one essentially special case of all these developments. You also algorithmically, many things have evolved around matchings, just like the Hungarian method, the augmenting path method, which led to things like the maximum flow algorithm. And then you have Tutt's characterization of graphs with a perfect matching. In fact, also Graco was very special for me, Graco 2001, because it was my first and last opportunity to see Bill Tutt. And it was very interesting because just shortly before 2001, the British government had declassified certain informations, and Tutt, for the first and I think the last time, spoke about his deciphering activities during the World War II. So this was really like a person which is fundamental in the area, talking about very important work, and for the first time this was very, very nice. And in 41 he gave this theorem about a good characterization of graphs with a perfect matching. For edge colorings, Wiesing's theorem is fundamental, which tells us that the chromatic index is between maximum degree plus 1 and maximum degree. And then algorithmically, the matching problem has been solved by Edmonds, and there are many nice structural things also that have been found. The chromatic index, as you know, is harder, even though you only have two possible values, as shown in Barholja in 81. Even in a very restricted case, it is difficult to decide which of the two values is the right one. Okay, so now let's look at restricted types of matchings. So the first restricted type are strong matchings, also called induced matchings. A matching is induced or is strong if the subgraph induced by the vertices covered by this matching is one regular, which means that you only have inside the set the edges of the matching. You might have edges outside, you might have edges between these two sets, but inside you have this one regular structure. And these matchings were first studied by Stockmeyer and Vasirani in a paper where they consider different variations of matchings, and they already showed in 82 the hardness of finding a maximum induced matching. Kathy Cameron studied this notion in detail. She had some refined hardness results and some polynomial time algorithms for restricted classes. And there are nice papers by Fordry, Jaffa, Shelp, and Souza on also structural aspects of these matchings. There is a very, very famous conjecture related to induced matchings, a conjecture about the strong chromatic index, the minimum number of strong matchings into which you can partition the edge set, which is widely open, a conjecture of Erdős and Nechetril, which states that a blow-up of a C5, you take a C5 and you replace every bubble by essentially maximum degree half many vertices, an independent set, would be the extreme structure, would have the largest strong chromatic index for all given graphs of a given maximum degree. And this would give us this bound here, 5/4 delta square. It is very easy to show something like 2 delta square by a greedy argument, and a breakthrough paper, even though the improvement over the obvious bound 2 is apparently minor, was by Molloy and Bruce Reed in 97. And for many, many years this was the best bound, and only very recently, essentially refining their technique, Henning, Brun Fujimoto and Felix Joos, and also Julk Postel and Marc Bonamy have improved these estimates. So let's look at the next type of restricted matchings. These are the uniquely restricted matchings. A matching is uniquely restricted if on the very same set of vertices covered by this matching, you don't find any other matching. So if you have this equality for two matchings, and this matching M is uniquely restricted, then the two matchings must actually coincide. And if you think about it, it is very easy to see that a matching is uniquely restricted if there is no M-alternating cycle, because this would allow it to construct another one, and if you're another one, you find such an M-alternating cycle. It actually comes from a problem related to matrices. If you have a 0-1 matrix, then some people studied the following problem. You are allowed to permute the rows and the columns independently, and you want to create a submatrix of largest possible size which has this structure. So 1's on the diagonal, 0's below, and whatever you like on top. And this corresponds to a uniquely restricted matching problem in a bipartite graph. And in this paper, Hershkovich and Schneider, they studied this problem on matrices. And this was later formalized in this graph theoretical language as a uniquely restricted matching problem in this paper by Marty, Hurst, and Levenstein in 2001, where they show many fundamental properties of these matchings, just what I said before. A matching is uniquely restricted if there is no M-alternating cycle, and more detailed results on bipartite graphs, a hardness result, so it's NP hard to find the largest uniquely restricted matchings even in a bipartite graph that has a perfect matching, and algorithms for many restricted graph classes. This notion was then studied later in papers by Vadim Levitt and Mandrescu in structural aspects. Mishra showed the hardness of approximation and gave an approximation algorithm. We will see his result a little later in the talk. And then very recently there is a very nice paper which solved the problem from Marty's paper. They described an algorithm to find the maximum uniquely restricted matching in interval graphs. As I said, there is whenever you have a notion of a matching, you can ask you can study the corresponding chromatic index. So the smallest number of uniquely restricted matchings into which the edge set can be partitioned. And this we studied with Ignazi and Julien in 2016. And the last type I will talk about are acyclic matchings. A matching is acyclic if the set of vertices covered by this matching induces the forest. And this notion was introduced by Goddard, Hedetnimi, and Lasker. And I denote it by nu1 because we also study some generalization of this. A graph is called R degenerate if every non-empty set of vertices induces a subgraph which has a vertex of degree at most r, which has minimum degree at most r. And we say that a matching is R degenerate if this induced subgraph is R degenerate. And this case here would just be the one degenerate case, because the graph is one degenerate if and only if it is a forest. Okay, so we started the corresponding matching number and the corresponding chromatic index together with Julien Baste this year. Okay, and there are some obvious relations. Every induced matching is acyclic, because it's just disjoint unions of K2s, so it's a forest. Every acyclic matching is uniquely restricted, because if the induced subgraph is a forest, it doesn't have any cycle, in particular no M-alternating cycles. And these implications imply inequalities among these matching numbers. So the matching number is greater equal to the uniquely restricted matching number, greater equal to the acyclic one, greater equal to the strong one. And the opposite things for the chromatic indices. And there is another relation, if you're R degenerate, you're also R plus 1 degenerate, which means that you have this sequence of inequalities relating these R degenerate matching numbers. Okay. Then the last type of matching I will look at is something that we discussed together with Jaime and Weverton. And we sat together and thought we had a very simple and nice question that we would solve on a lazy afternoon. And the question was the following. If you are given any graph, does it have a matching whose removal, now you just remove the edges, whose removal leaves a forest? This sounds very simple because the graph has very few edges, and you think, okay, if you work the other way around, take any forest and add the edges of a matching, this feels as it should be something which has a simple structure. Yeah? So the way I present it already tells you that the truth is probably not quite this one. And we also studied the similar question for the bipartite case. So given a graph, does it have a matching such that removing these edges, you have a bipartite graph? Okay, so today I will speak about some work on approximating the induced matching number using local search algorithms. I will also speak about an approximation algorithm for the uniquely restricted matching number and show some upper bounds on the uniquely restricted chromatic index, bounds on the R-degenerate chromatic index, and answering a question of Goddard, Hennenfent, and Lasker. We show an algorithm for the R-degenerate matching number in caudal graphs. And eventually I'll talk about the removal problems, decycling with the matching and bipartizing with the matching. Okay, and here you see all the co-authors also mentioned in the beginning. So let's start with this approximating the induced matching number using local search. So what do we know about approximating this parameter? So first of all, it is APX hard. So the maximum induced matching problem is APX hard for every D-regular graph, D at least 3. And this remains true if you restrict to bipartite graphs, which was shown by Dabrowski, Demange, and Lozin. And also in very restricted graph classes, such as line graphs, Clawfree graphs in particular, the maximum induced matching problem is difficult, is NP hard. Okay. On the other hand, there are some approximation algorithms. Duckworth, Manlove, and Zito showed that the maximum induced matching problem restricted to D-regular graphs has a D plus constant factor approximation algorithm. So there is an earlier result by Zito which has a different constant. This is why I don't give the value here, but this is something like a small value, like 1 or 2. But this result is actually essentially trivial. If you don't really care about whether this 1 or 2, then you have a 2-line proof of this, because if you are in a D-regular graph, every induced matching has at most this size. Because if you look at the edges in that matching, this vertex is incident to D minus 1 further edges that don't go to any of these. And this vertex also has D minus 1 further edges incident to this. So here you have a set of 2 times D minus 1 plus 1 many edges. And you can do this for all these edges in your matching, and all these sets are disjoint, which gives you this estimate, this upper bound. On the other hand, every maximal, inclusion-wise maximal induced matching has at least m divided by 2d square minus 2d plus 1 many elements. And this is also very simple, this argument, because if you look at any edge that you have in your maximal induced matching, how many edges are forbidden in your matching because of this? So, well, you have like D minus 1 neighbors here, and each of these has at most D edges around it. So you have 2 times D minus 1 times D edges which are forbidden because of this edge in your matching, plus 1 counting this edge itself. So this is exactly the fraction that you see there in this denominator. Okay, so putting together these two things, you already have an approximation factor of D minus 1/2 plus something. So that's already the proof of this approximation guarantee. So it's really obvious. And now we would like to improve it, or people wanted to improve it. It doesn't really make much sense to improve this factor here. So the only thing that is interesting to reprove would be the dependence on D. And the only real breakthrough result doing this is a paper by Kotov and Levenstein from 2006, who showed that restricted to D regular graphs, you can do better. You can do with this factor here, 3/4 times D plus a little constant. And exploiting their method, I will explain it in a bit, we were able to answer a question by Dabrowski and Lozin, namely, if you do this for bipartite graphs, or more generally for C3, C5 free graphs, you can do even a little better. You can push the factor down to what you see here on this slide. It's not an impressive improvement, but it's a small improvement. Okay, how does it work? It works by looking at conflict edges and private conflict edges. So conflict edges is essentially what I explained, what I talked about in this picture. So if you have an edge in a graph, E, then the set CEG of conflict edges is essentially the closed neighborhood of this edge in the square of the line graph of G. So you take the line graph, you take the square of the line graph, you take the neighborhood, and then you add the edge itself. In other words, you take all edges of your graph such that the distance in the line graph between your edge E and this other edge is at most 2. These are all edges that cannot be together with E in an induced matching. And the number of these is just this little c. And then the private conflict edges, denoted by PC, of some edge in relation to some set of edges, are just the conflict edges of this individual edge that are not conflict edge of any other edge in that set. These are the private conflict edges. Okay. Now let's look at a way of counting these things. So if we have an edge xy here, then we can look at the neighbors or the vertices at distance 1 from this set, from this edge. Some are just neighbors of x, some are neighbors of x and y, some are neighbors of y. And the number of common neighbors, let's say, is nxy. And then we have inside this set, we have some edges, and the number of the edges inside this set, let's say that it's mxy. Okay, so the number of these is mxy. And then we look at the vertices at distance 2 from this edge, and we have edges between these two sets. And where do we have the conflict edges? In fact, the edge itself is in conflict with himself. The incident edges, the edges in this set here, and the edges between these two sets. These are all the conflict edges. And how many do we have? We have 1 for this edge here. And then how many vertices do we have in this set? We have like this many vertices in this set, and every vertex in here generates at most d further conflict edges, but we double counted some of them, namely those which have both endpoints in here. So we have to subtract what we double counted. And how big is this cardinality here? It's essentially 2 times d minus 1 minus the number of common vertices, common neighbors. So it's exactly this quantity here. So you see this factor that we already saw before, and then if you have many common neighbors, you have to reduce it, and if you have many edges in this level, you also have to reduce it. So these numbers here tell you how much you have to reduce it. Okay. And then the algorithm of Kotov and Levenstein works by combining a greedy strategy with a local search. And what does the greedy strategy do? It greedily adds edges to an initially empty induced matching, and it only does so if if they are not too expensive. What does it mean? Adding an edge, you have to remove some other edges. It will forbid some remaining edges, and you only do it if the number of edges you lose is not too big. And this is called greedy alpha, and alpha is this number that tells you what is not too expensive. You start with an empty matching, you start with your graph, and then while there are still edges that are not too expensive, such that adding this edge you only lose at most alpha of the remaining edges, you do it, you add these edges to the matching, and you remove all the conflict edges from your graph, and you iterate, and you do it until either you have consumed all edges, or all remaining edges are too expensive. If you would add them, they would cost more than alpha many edges. And you return the matching that you have constructed so far, and you return the remaining graph, because you might still have some edges, each of which was too expensive, but you can still do something with these edges. That's the first part. And now comes a local search strategy, which is you want to construct a maximal induced matching, and on top of that you want to look at changes. 1 matching edge is removed and 2 replace it. So you repeat this procedure here. Whenever you can add it, whenever you're not maximal, you just add the edge. And whenever you can trade 1 element of your matching against 2 edges which have not been in the matching before, you also do this. And you repeat this local search until there is no more improvement possible. Okay, and that's combining these 2 things and choosing alpha to be the right number gives you this algorithm of Kotov and Levenstein. So now let's look at the fundamental ideas for the analysis. So what happens after the greedy phase? After the greedy phase, the remaining edges in this residual graph are all too expensive. So each of these remaining edges has more than alpha conflict edges. G prime is what you get after this residual graph. And if you look at the output of local search on this applied to some graph G, and you do the following counting. So you count the number P of pairs where E is an edge which is in your matching and F is an edge which is in conflict with E. Yeah? So you apply local search to any graph G and you look at the output and you count these pairs here. What do we know about this? Double counting P, first of all, tells us that P is at most this number. It's obvious because if you fix the first coordinate, how many choices do you have for the second coordinate? Exactly this many choices. And then you just sum over the possibilities for the first coordinate. That's obvious. And you have also a lower bound, and the lower bound is M of G. Why? Because for every edge as the choice for the second coordinate, it is in conflict with some other edge in your matching because it is maximal, inclusion-wise maximal, so you have this inequality. So, and now what they do is they say, okay, this inequality here can be improved by saying that typically for some choice of the second entry, you might have more than one choices for the first entry, let's say at least two, but you don't have this exactly for the private conflict edges. For the private conflict edges, if this F is a private conflict edge of E, there is only one pair which has second entry F. And if you look at this inequality, this is what they use to improve the approximation guarantee. So now what you have to do is the following. You move this term here to the right-hand side. You have an upper bound on this quantity here. Actually, that's the upper bound I've shown to you, which is essentially this factor minus the correcting terms. And now you have to do the following. You have to upper bound the number of private conflict edges. And if you can do this in a good way, upper bounding these two sums, then you get that the number of edges in the matching produced by local search is relatively large. So why would you have, or why should it be possible to bound the number of private conflict edges? So the key is to choose this value here right, and you choose it very close to this maximum possible value here. If the number of conflict edges is close to this maximum possible value, then it has some structural consequences. First of all, x and y, the two endpoints of the edges in your matching, cannot have many common neighbors, because otherwise just the neighborhood is too small to generate sufficiently many conflict edges. And secondly, you can't have many edges inside that neighborhood because these are double counted, and if you double count too often, then it's also not good. So you get a very clean picture, and the larger alpha, the closer alpha is to the factor 2 or 2d square, the cleaner this picture gets. And then you use this structure to show that you can't have, given this structure, you can't have too many private conflict edges. So a large value of alpha allows a better bound on the number of conflict edges. And now you see what you have to do. So choosing alpha big makes this quantity here relatively large, but improves the upper bound on this. And now you have to find the right choice to balance these things out and get the right factors. Okay, so now we did the following. We wanted to look at local search alone and exploit the same mechanism. So you upper bound the number of conflict edges and you want to upper bound the number of private conflict edges, and this time using structural properties of the graphs, just like being bipartite or having no short cycles. And here are the kinds of results that we obtain. So for C4 free graphs and for graphs of girth at least 5, deregular in every time, you have approximation guarantees of this form, which are already better than the 0.75D that you have from Kotov and Levenstein. And for C5 free graphs, you already have this factor, even if you don't do this greedy preprocessing, which gives you this nicely structured graph. And we also looked at claw free graphs. And also here, just doing the local search algorithm gives you an improvement of a factor of 2 over the approximation guarantee. So these results exploit this basic inequality chain and do counting based on the structure of these graphs in order to bound the number of private conflict edges. This case of claw-free graphs is a little special because here we can show that even if so local search creates a maximal matching and also 2 maximal in the sense that you cannot trade 1 edge inside against 2 edges outside. But if you just do a maximal matching, this is already almost as good an approximation guarantee for claw-free deregular graphs as doing the full local search algorithm. So if you look at these results, this is what we obtained in this paper. It would be interesting to see if you can improve them by combining them with the greedy preprocessing. Because here we only look at we don't do it with the preprocessing. We don't exploit that there is a residual graph which has a large number of conflict edges for every element. And we just use the forbidden induced subgraphs to get the counting right. But there might be further room for improvement if you combine these 2 techniques. But it's not obvious how to do this, because sometimes the configurations, the extremal configurations that you get from here would not be forbidden by increasing the values of alpha or setting certain choices for this alpha. Okay, so this was about approximating the induced matching number, and now let's switch to the uniquely restricted matching number. We want to approximate this parameter, and we want to do this in bipartite graphs because it is already hard for bipartite graphs and even for split graphs. And even more so, it is, as Mishra showed, it is APX complete for subcubic bipartite graphs. And what he also did is he described a factor 2 approximation algorithm. And together with Julien and Ignazi, we improved this approximation factor, which would be 1/2 in this notation. We improved it to 5/9. So we have this result here for a connected subcubic bipartite graph. We can find in polynomial time uniquely restricted matching, which has at least 5/9 of the maximum possible cardinality. And this result has a very long proof. A part of it is rather beautiful, and then there is pages of ugly case analysis. And the beautiful part also leads to this second result, which I will explain to you. The C4-free case, if we forbid C4s, then we can do the analysis not just for subcubic graphs, but for any value of the maximum degree, namely connected C4-free bipartite graph, maximum degree at most delta. Then we can find a large uniquely restricted matching in polynomial time, and large means this quantity here. If you plug in 3, then you get exactly 5/9. So how does this work? It is based on this lemma. So what does the lemma say? If we have a connected C4-free bipartite graph with the maximum degree delta, given partite sets, and we have the following structural restrictions, every vertex in the partite set A has degree at least 2, and some vertex in the partite set B has degree less than delta. So the first condition is not really an important restriction, because if you have a vertex of degree 1, then you can put the incident edge always into some large uniquely restricted matching. You can just remove this edge and the 2 incident vertices and keep on repeating. Yeah? The second restriction is just a technicality, because we need it for the first step of the algorithm. Because after we have done the first step, we'll always find a vertex which satisfies the properties we need. So this is something we can ensure also easily. And then if you have these things, then you find a matching, a uniquely restricted matching of this size. And now, instead of the uniquely restricted matching number, here we have the cardinality of A, which is certainly an upper bound on any matching number. So this gives you what you want. Actually, it gives you slightly more. And you can also find this matching in polynomial time. And how does the algorithm work? So we, given this graph, we maintain pairs, UM. U is a subset of the vertices, M is a uniquely restricted matching. So we have A and B, and then on the left-hand side we have U, and on the right-hand side we have the complement of U, and then M lives inside U, so these matching edges are part of the matching that we'll output eventually. And then there are some conditions, namely the vertices in B intersection U in the bottom left, they have no neighbors on the top right. And the vertices on the bottom right, in B without U, they have all at least one neighbor in the top right. So you have these two restrictions that you see illustrated in the figure. Okay, so, and we maintain such pairs. And then we look at the vertices in this area here. So we have S vertices that are covered by our matching. We have D vertices which have a neighbor in the bottom right. And then the remaining vertices, F of them, have no neighbor in the bottom right. And we maintain these pairs such that they satisfy a certain inequality, this inequality here. So this will eventually give us the approximation guarantee, and we only do extensions that once you start with a set satisfying this inequality, after the extension the inequality is still valid. Okay, so how does it work? We start with both things being empty. On both sides of the inequality you have 0, so it works. And then as soon as the set U does not cover all the vertices, we can still do an extension step. We extend U to U prime and M to M prime. And once the set U has all the vertices, then the inequality that we maintain will give us the approximation guarantee. Why? So it was, you see it here again. Eventually, the number of edges that you return is exactly this value S. It's the vertices in A covered by the matching edge. And then this is D plus F. So why? So U is everything. So every vertex not in A, not covered by the matching, has no neighbor outside U. So D is all the remaining vertices in A, which is A minus M, and F is 0. And this is at least this quantity, sorry, it's all F. F is all this quantity and D is 0 by definition. And you have the same thing here. And now if you look at this is an inequality involving the cardinality of M and the cardinality of A. And if you solve it, you get the thing that you want. Okay, so how does it work? Suppose we are not done. Then we find a vertex in B without U. That has, in the bottom right, we find a vertex that has a neighbor in the top right. At least one, and at most delta minus 1. And assumption on a vertex in B of degree less than maximum degree in the first is just for the first iteration of this choice. And then you do it you choose this vertex, minimizing the number of neighbors in the top right of the picture. Okay, if this number is 1, then it looks like this. So here we have our partition, and here we have this vertex, which has exactly one neighbor in the top right, and we would like to move these two guys into U. But so the top guy, this guy would also be moved into U, and since everybody that is in here still needs to have a neighbor up there, we have to move to U also all those guys such that he's the only neighbor in the top right. Everything has to be moved to U. And this extended set will be U prime. So now we want to extend the matching. And for the extension of the matching, we look at those vertices here that have neighbors up here and the other ones. And now you see why C4 freeness is a good thing, because all these vertices have this common neighbor, and this means that if these two vertices have neighbors up here, then these edges form a matching by C4 freeness. And now, in order to extend our matching, we either use these edges here, or depending on the values that we see, or we use one of these edges between some vertex here and this vertex there. The other case is also a similar extension. If the vertex in the bottom right, so this vertex here, has more than one neighbor up here, then we can move this guy and all these guys to this set here. And it still works because C4 freeness once again helps you. If you look at a vertex which is here, how many neighbors in the top right does it lose? How many common neighbors does it have together with you? at most one common neighbor by C4 freeness, but everybody in the bottom right at this point of the algorithm had at least two neighbors in the top right. So we don't get any guy down here with no neighbor up there. And now we check for this condition. If this vertex has a neighbor here, which is not incident with the matching M, in fact, it has a neighbor, and a part of that, every neighbor in here is not incident is not incident with M, then we can actually use this edge in order to extend our matching. Yeah? And the reason is, let me just explain it at this point, why adding this edge still keeps a uniquely restricted matching. So you have these edges which are uniquely restricted matching, and now imagine you add this edge here. If you created an M alternating cycle, it must use the new edge. And now you ask yourself, if you go along this cycle from here to there, this belongs to the matching. Now you have to use an edge which doesn't belong to the matching and which goes back to these vertices here. Yeah? But the condition tells you that no neighbor of this guy in this set is in here. So you can't go back, you can't create, you can't close an M alternating cycle. And otherwise, if this vertex doesn't exist, you can just take one of these edges, and that's it. And looking at the numbers, you see that the inequality is maintained and everything works nicely. If you now allow C4s, then all nice parts of this argument break down, and you have to look at many local configurations that we only could do by limiting the maximum degree to 3. Okay, we also did some upper bounds on the uniquely restricted chromatic index. And here's the main result, which is actually very nice, because it is a similar question like this problem of Erdős and Neschetral for the strong chromatic index, which is widely open and only very small steps require a lot of work. But here in this situation, for the uniquely restricted chromatic index, we can give the exact result and we can characterize all extremal graphs. It's delta square is the upper bound, and you have equality if and only if you have the complete bipartite graph giving this. And the proof is actually not very difficult, so I can explain it to you. Now, so we have a connected graph of maximum degree at most delta, and we want to partition the edge set into uniquely restricted matchings. So we take any linear ordering of the vertices, and we assume for I from 1 up to n minus 1 that the edges incident with this initial piece, u1 up to ui minus 1, all the edges incident with that set have already been assigned a color. And now in the next step, we color the still uncolored edges incident with the next vertex ui. So let's say you have d of them, and we want to use distinct colors. It has to be a matching. And as a second rule, what we do is we avoid any color that has already been used on a previously colored edge incident to some neighbor of u. So let me show you a picture to make it more clear. So the edges leaving this set have already been colored at this moment. This guy has some neighbors to the left and some neighbors to the right. He has d neighbors to the right and at most delta minus d neighbors to the left. These edges actually are already colored because they're incident with the vertices in here, and these edges have not yet been colored. Now we have to color these edges here using distinct colors, and we avoid all colors that we see on these edges. The edges that leave these vertices here, and also the edges that are incident with vertices with neighbors on the right of this guy, but which come from here, which come from inside the set, which go to the left. Okay, so how many colors do we need? It's a very simple thing, a very simple count. This guy has d neighbors to the right, and every neighbor to the right has at most delta minus 1 already colored incident edges. So this gives this many colors that we see on these edges here. This guy has at most delta minus d neighbors to the left, and every neighbor to the left forbids at most delta many colors. Yeah? And then we have d edges here. So if we add to these two upper bounds on the number of colors that we have to avoid, the number of colors that we need for the edges, then it would be fine. And if you evaluate this expression, that's exactly delta square. So it figures out nicely. So this works. It colors all the edges of the graph, but you still have to prove that it satisfies all conditions. So you have to prove that every color class is a uniquely restricted matching. And that's actually a very cute argument. Assume that this is not the case. Assume that one color class is a matching, of course, because we never create incident edges of the same color, but has an M alternating cycle. That would be the obstruction. And if you look at this M alternating cycle, it has a leftmost vertex, and this leftmost vertex is this guy here. It has the smallest index in our linear ordering. And we organize the indices in such a way that this edge here does not belong to the matching, but the matching edge incident with this vertex comes from the back, comes from this guy here. So the first edge is not in the matching, the second edge would be in the matching, and so on. That's just a symmetry breaking of the way we write down this cycle. Okay, and then of course this is because we chose the leftmost vertex to have this index, and then the coloring rule implies this inequality here. It's very easy to see that if you look at the coloring rule, avoid this and these colors, you get this inequality chain. And then there is a nice thing, if you exploit these coloring rules inductively, and you start with an inequality chain of this type with the shifted indices, then you get the same inequality chain for the next index. So it propagates. And in particular, it tells you that if you look at the index Ri, it is smaller than Ri plus 1, smaller than Ri plus 2, smaller than Ri plus 3. But you can go around this cycle, so eventually you get this contradiction. You get this increasing chain of indices, and going one more step, you get this contradiction, because all these indices would have to increase all the time, and it is not possible on the cycle. Okay, and for the characterization of the extremal graphs, you just take such a good coloring with delta square colors, minimizing the number of times you use one specific color, and then you ask yourself, why can't, if you look at an edge colored this way, why can't you use a different color there? And this has some structural implications around this edge and tells you that the only way that you're forced, you cannot reduce this number any further is when you have delta delta. There is a very nice alternative way of proving this. So this proof starts with a graph and just immediately generates a coloring, which is okay, whose color classes are uniquely restricted matchings. But another strategy would be you take a classical edge coloring, so you partition the edge set into matchings, and now you split every matching, every color class, into uniquely restricted matchings if it is not already uniquely restricted. So, and if you look at bipartite graphs, for instance, you could use Koenig's theorem to say that you start with a delta edge coloring, and then you look at the delta color classes you have there, and you ask yourself, how do we have to split this to get a uniquely restricted edge coloring? And there is a very nice thing that we can do, inspired by Lova's elegant proof of Brooks' theorem. We can show this result here, namely, if you have a connected bipartite graph, which is not our extremal graph, and you take any matching in there, which is not necessarily uniquely restricted, then you can split it, then you can partition it into at most delta minus 1 many uniquely restricted matchings. And this tells you that if you are in a bipartite graph and you exclude the only extremal graph which is bipartite and which needs delta square many colors, the number drops not just by 1, but immediately drops by delta. Because, as I said, using Koenig's theorem, you can first color your bipartite graph using delta color classes, and if it is distinct from car delta delta, each of these generates delta minus 1 many uniquely restricted matchings, and you get this bound. So that's nice. Okay, so now okay, so here you see delta is at least 4, and this is not a coincidence. Actually, the thing fails for maximum degree 3, which is somewhat strange. Upper bounds on the R-degenerate chromatic index. If you look at this, you immediately know that this is a variation of this greedy argument. And the fact is that we are not completely satisfied with this, because if you just exploit this greedy argument, or the maximality of the matching you look at, you get something which is only tight in the case of acyclic matchings, where an R equals 1. And in this situation, it gives the right value, and again you can characterize the extremal graph, K delta delta. But apart from that, for larger values of R, we know that this bound is not, there is no graph satisfying this with equality. So we don't have the right bound in this case. So this would be definitely something that has to be investigated further, and where nice things are maybe possible, better bounds are possible for this thing. Okay, now let's look at this thing answering the question posed by Goddard, Hennenfent, and Slater, Lasker. They asked about an algorithm to compute the acyclic matching number in interval graphs, actually. And what we do is, more general, we show how to calculate the R degenerate matching number in chordal graphs, which is a superclass. How much time do I have? 10 minutes. So, sorry? Nearly, which means less. Yeah. Okay. Or means more. Okay. So this is why I introduced this little thing there, and I will now click on it to jump this part. But I can briefly tell you what we do. If you have a chordal graph, then of course the tree width is not bounded, but it has a tree decomposition where every bag is a clique. It might be very big, but every bag is a clique. And now you can do dynamic programming just as you do it for bounded tree width things on a tree decomposition with complete bags, because what you're looking for is an R degenerate matching. Meaning that if you look at the set of vertices covered by this matching, it induces a subgraph which has a vertex of minimum degree less than R. This tells you that from every bag, you can only pick a bounded number of vertices, bounded in terms of R. So even though the bags might be as big as you want, might be of linear size, since you only have to look at bounded subsets of this, you can just enumerate, just as you always do it, for bounded tree width dynamic programming algorithms, all relevant sub-solutions, and to paste them together in this typical bottom-up way and obtain your algorithm. So to make this precise, you have to tell exactly what is a partial solution in such a way that you have this recursive way of computing the values or the partial solutions going from the bottom up in your tree. And this is very, very technical as usual, but I can just tell you that it's just the same way as always. And then the result that you obtain is this. No matter for which fixed integer R, for a given chordal graph, you can find the maximum size R degenerate matching in polynomial time, just by this procedure. Okay, so now let me go to this part here. Decycling and bipartizing matchings. So here, let me say again what it is. It is slightly different from the matchings we looked at before. For the matchings we looked at before, we had conditions on the subgraph induced by the set of vertices covered by the matching. Now what we want to do is we take the graph and we want to remove the edges of some matching such that the remaining graph has a certain structure. Okay, let's say that Fm is the set of all graphs that have a matching such that removing the edges from this matching M leaves a forest. So F for forest, M for matching. And let's say that Bm is the same thing for bipartite. So all these graphs have a matching such that removing these edges you have a bipartite graph. And now let's collect some very simple observations concerning this Fm. So if your graph consists of the edges of a tree or a forest plus the edges of some matching, it is very sparse. If you pick any subset of vertices, you have at most cardinality -1 many forest edges in there, and you have at most cardinality half many matching edges in there. Which means that, okay, I'm jumping ahead of myself, but let's already show this. Which means that you have essentially something like at most 3 half times the order of this subset many edges in there. Yeah? And the -1 comes from the forest part. Okay, if a graph is connected and it has a matching whose removal leaves a forest, then it also has a matching whose removal leaves a tree. Because you can just leave some edges in there that ensure the connectivity that was destroyed. So for connected graphs in FM, we can actually just look for those things, those matchings whose removal leave a tree. The second thing is what I explained before. The local density is always small. And these two things, it suggested to us that it should be simple to decide this. But then there's also this very simple observation. If you have a subcubic connected graph, then it belongs to this class. It has a matching whose removal leaves a forest, or leaves a tree in that case, if and only if it has a spanning tree, which is the tree that is left after removal of the matching, such that all end vertices of that tree have degree at most 2 in the graph. It's obvious that this is necessary, because if you look at the tree that remains after the removal of the matching, and you look at an end vertex of that tree, it has degree 1 in your tree, but if the degree in the full graph would be at least 3, the matching would have to contain 2 edges incident to that guy, which is not allowed. So the necessity of this is obvious, and the sufficiency is also implied by the fact that this graph you look at is subcubic. So this is just like a 2-line statement. But this is the key observation to allow a very simple hardness result, a hardness proof for this. Because what we now do, so if you look at this, what does it mean? So you have a spanning tree such that all end vertices are of degree at most 2 in G. So now what we would like to have is, this is essentially, it restricts the set of vertices from your graph, which can be a leaf in your tree. And this is close to Hamiltonian path, because if you would say there is a very small set, maybe just 2 vertices, such that these are the only 2 vertices which have degree 2 in your graph, asking whether there is a spanning tree having all leaves of degree at most 2 is the same as asking, is there a Hamiltonian path connecting these 2 specific vertices? And once you have realized this, it's very simple to show the hardness of this problem. If you have a given 2 connected planar graph, it is NP complete to decide whether it is in FM. And it goes like this. You take your favorite Hamiltonian cycle NP completeness proof, in this case for 3 connected planar cubic graphs, and then you look at the construction and you realize, so one construction that many people know is this circular construction where you have like parts setting the variables, true or false, and then you have another part where this corresponds to the clauses and you have some edges linking this. And then the thing has a Hamiltonian cycle if and only if the corresponding satisfiability formula is satisfiable. But then if you look at this construction, you have these gadgets corresponding to the variables, and each 2 gadgets are linked by an edge. And this edge, if there is a Hamiltonian cycle, will always make part of this Hamiltonian cycle. So what you do is you take this proof, and construction which is similar, and you realize that some edges would be on all Hamiltonian cycles, whether there are 0 many or at least 1. And then you remove this edge, so the graph was cubic, now you have a subcubic graph which has exactly 2 vertices of degree 2, and asking whether the original graph has a Hamiltonian cycle is the same as asking whether this graph, where you have removed this edge belonging to every Hamiltonian cycle of this guy, if this graph has a Hamiltonian path linking these 2 vertices, and that's the proof. So it's, once you realize these very simple structural properties, the NP completeness proof is rather simple. We have some positive results, mainly for if you forbid certain small induced subgraphs, the typical candidates, CLOR, POR, P5, free graphs. We can do it for chordal graphs, we can do it for C4 free distance hereditary graphs. These are typically reduction algorithms or extension algorithms if you look at the other way around. And then for the bipartite case, if this thing was hard, then it would be surprising if the bipartization problem would be easy. Also, the bipartization thing is hard for a similar class of graphs. Even the maximum degree can be bounded here. And also here we have some partial positive results. I think that's a good point to stop.
So do you have questions or remarks? Yes,
well, I checked with Frederic, so I think I will ask you this question. There is a point during our talk, you mentioned many results, was very nice, beautiful. But then there was a point where you mentioned this elegant proof by Lorenz of Brooks theorem.
Yeah.
And the Brooks theorem is about
vertex.
Yeah, so I was a bit
okay.
mysterious to me.
How it works? Okay, so the idea. Yeah. So. Yeah, for this proof of Brooks theorem by Lorenz, what you have to do, you have a graph of maximum degree delta, and you assume that it is not the complete graph, and then you have to show the existence of a spanning tree, which has the following structure. So it has a root, and there are two neighbors of the root, which are leaves of the tree, and these are non-adjacent in your graph. That's important. And then the other thing just hangs down here. And now, when you now you can use this spanning tree to color your graph greedily from the leaves up. And every time you color a vertex, which is not the root, it has the parent, which is still uncolored. So if you just do greedy coloring, every time you are not the root, you still have an uncolored neighbor, which means that you can do it with delta colors. These two guys are colored before him, and they are non-adjacent. Yeah? And you actually start by coloring these two vertices. And since they are non-adjacent, they get the same color. So you first color these guys, and then you go from the bottom up, coloring the remaining vertices, always having an uncolored neighbor. And once you reach the root, you don't have an uncolored neighbor, but you have two neighbors colored the same way. Yeah? And now what you have to do here is you just have to exploit the same thing here. So we want to look at spanning trees which contain the edges of our matching. And then we want to greedily color the edges of our matching, setting aside something like this, things that are good, in such a way that always we have an uncolored edge. And for the root, we have two things which are colored the same. So you just have to adapt this idea from vertices to edges. I have a question to you. During your talk, who asks your question?
So are there other questions or remarks? This one? Yeah.
If you take, instead of matching, you take induced matching, the complexity of the problem of removing this special matching becomes harder.
If you do this removal problem for the, this should be hard as well. This should be hard as well. So for instance, if you ask, is there an induced, maybe not. Yeah? Is there an induced matching whose removal leaves a forest?
Yeah, it's hard because we can use the sum reduction.
By the maximum degree thing. The matching is actually, is it true? Yeah. Okay, yeah. By the, yes, it's true. So but there might be larger classes for which you can do it in polynomial time. So the hardness result is still true if for the specific case of induced matchings. For the other ones, you can maybe do similar things. And but there might be different classes for which you can do it in polynomial time.
I myself have a question. When Kathy Cameron worked about maximum induced matchings, she used the fact that maximum induced matching in the graph corresponds to stable set, independent set in the square of the line graph. So, and then she had several such reductions. For instance, if G is quartal, then L of G squared is quartal. There are many other cases. Weakly quartal. If G is weakly quartal, then L of G squared is weakly quartal, and so on. Can you Can you use this approach here for your own?
This is implicitly used. So for instance, if you think about the definition of conflict edges, this is the closed neighborhood in the square of the line graph. And if you do counting of these conflict edges, of private conflict edges, you essentially exploit structural properties of the square of the line graph of an arbitrary graph. So if you now restrict, if you start not with an arbitrary graph, but you start with a chordal graph or things like this, then exactly as you say, sometimes looking at the square of the line graph, the original structural property implies nice structural features here. But this is, in some sense, it is done implicitly. For instance, when we look at this, if you think about this result by Molloy and Reed, this is essentially a statement about cliques and corresponding colorings in squares of line graphs. And the fact that you can improve below this factor 2, this trivial factor 2, essentially exploits the fact that the square of the line graph of any graph has some special structural features that allow a better estimate. So it is not maybe stated explicitly, but it is used in these counting arguments.
Are there other questions or remarks? If not, let's thank again.